Okay, so this is a quick one about spatial frequencies, which is just purely to help me. Let's imagine we have a plane wave, or approximately a plane wave, traveling horizontally in this direction, and my lines here represent peaks in the kind of electric field. So maybe the electric field's going that way here, that way there, etc., etc., and there's nothing in between, and it's traveling along. Now let's imagine that there happens to be a line of pixels that this kind of edge of the electric field happens to, graze along as it travels, and we take and this pixel detector takes an image. Then what we're going to see is the pixels, and let's say the pixels aren't binary, they kind of do grayscale as well. We're going to find it's going to get nothing here. This is like strength, and we're going to get at this moment when this image takes place. Imagine, in the ideal case, we can take a perfect image. We're going to get something in terms of the intensity that that looks like this, where it would be a sort of peak wherever the electric field is maximum, because the detector can't know which way it's going, and there would be nothing where it's moving. In other words, my detector would pick up a spatial frequency. This is a spatial frequency, and we represent them, spatial frequencies, as k, which would be 2 pi divided by lambda. So it's the sort of reciprocal wavelength, or the amount of phase you gain per meter. Right, now with this detector, let's imagine that this time I've got the same sort of detector, but this time somehow the wave is traveling this way. Same wavelength, but it's traveling this way, like that when it hits. Then, and this is sort of, it's going through, let's say it's going through, it's not really affected by my detector, but the detector sort of picks up a sample of it as it goes through, like that. Then what we're going to do now is we're clearly going to pick up a spatial frequency like this, but a longer spatial frequency. So if this happens, my spatial frequency is going to be increased, which means my k is reduced. K is smaller, and we can clearly see that it's picking up less phase. Now that was, and I could also imagine if the wave was going that way, it would be like that as well. Now I would get the same wave, same pattern of course on my detector, same spatial frequency, as if my wave was going this way. So in other words, these two waves would be, I actually couldn't tell which one it would be from the detector, from the spatial frequency, from the point of view of the detector. I couldn't actually tell which one it would be. So we could, if we knew, if we had some way of knowing which way it was going, we could indicate it with a positive and a negative k value to indicate whether it's going this way or whether the wave's going that way. In the most extreme case, I could actually have a wave going this way, and then my detector wouldn't see a wave at all, it would just see them all on, and it would be entirely DC component, in which case we would say k equals 0. We're not doing any phase. So in this way, my spatial frequencies, the plane waves, as they interact with my pixel detector, capture something about the direction and the propagation of the light. Now, consider the following situation now. Let's imagine I have that each point here represents a pixel, and then I don't detect anything between them. But let's imagine that these detectors are point detectors, they have no size. Then clearly I could detect, if I had this wave hit, where then it would seem to me to be DC. I wouldn't be able to detect any variation whatsoever, even though there was a wave and there is a spatial frequency. So this is an example of aliasing, where what happens is I would, if you like, this appears to be a DC, a very low frequency, k=0 wave, and yet it's actually much higher frequency, but the if you like, the energy, the information of this particular wave will, on my detector, will be added to a DC wave. Because if I simultaneously had a wave like this at the same time, that would also create a flat wave, which would be added to that. So I couldn't distinguish between those two. Imagine if another example of aliasing. Imagine if I had my pixels like this, and so let's imagine I have bright. These would be the maximums like this. This is right on the kind of edge of being able to detect it, but I would detect it because I'd have bright, dark, etc., etc. Another wave, which would also be like this, would be if I had bright, dark, bright, dark, bright, dark. So this would be another example of where I'd had aliasing. So these higher frequency waves would be in the energy, as far as this detector would be concerned. All of these waves, this one and this one, where I got so ones like this would all end up, their light would end up going into this pattern of pixels. So again, I couldn't tell between them. So again, this would be an example of aliasing. Now we could also apply this to a two detector array of pixels in much the same way, as well as a one detector array. And if I now observe in my snapshot that these pixels were illuminated like that, then there are many combinations of plane waves that could have done that. I could have, for example, have had, if you like, kind of vertical waves like this, plane waves, which could have sliced in that way, travelling along that way. Then again, they could have been travelling on that way. Then again, they could have been angled. Now, if I have I need extra information in order to know what plane wave corresponded to this particular pattern that I'm seeing. But if I know that the wavelength is fixed, I've got some particular wavelength, that actually simplifies things quite a lot. Because if the wavelength is fixed, then I know that k squared is going to be kz squared plus kx squared plus ky squared. So that will then mean I can, now, next assumption I have to make is that the frequency isn't too high, so I get aliasing. So I have to assume that there's only one frequency here, otherwise I can't distinguish between them. But if there is only one frequency here, then I can pinpoint, using the fact I know the wavelength and I know this fact, and I know then I can pinpoint what the plane wave is. Of course, I can't pinpoint whether it's going this way or going that way. That would depend upon its sign. So in my Fourier spectrum, I need to have positive and negative in order to distinguish the direction that it's going in. So, right, yeah, finished that.